Welcome. Today, we find out how many trailing zeros appear in the factorial of a number. For example, how many zeros are at the end of 35 factorial? Instead of computing the huge factorial directly, we'll use a unique mathematical trick. Trailing zeros are created by factors of 10, and each 10 is a pair of 2 and 5. Since factorial since factorials contain a ton more 2's and 5's, we only need to count how many 5's and powers of 5 divide into numbers up to n. We'll write a short and robust JavaScript function that does exactly that. Fast, memory light, and safe for large inputs. Let's go. So, rather than multiplying everything out and counting zeros, we count how many multiples of 5 are present, where each contributes at least one 5, and then we add extra counts for multiples of 25, where each one contributes a second 5, and so on. That gives us a logarithmic time solution that's perfect even for large n. This function first validates n so you don't accidentally pass weird values. The for loop multiplies I by 5 each iteration, counting how many multiples of each power of 5 fit into n. We then accumulate these quotients into count. That final count equals the number of trailing zeros in n factorial. It is compact, clear, and runs in big O log 5n time. Counting floor, where n divided by 5, gives the numbers that contribute at least one factor of 5. Counting floor n divided by 25 adds those numbers that contributes a second 5, and so on. Summing those gives the total number of factor minus 5 occurrences. And because there are always plenty of factors of 2's, that equals the number of trailing zeros. Here, the table shows how each power of 5 contributes. For 35, floor 35 divided by 5 is equal to 7, where numbers like 5, 10, 15 up to 35. And floor 35 divided by 25 is 1. The number 25 contributes an extra 5, so the total is 8. This matches the sample outputs without computing big factorials. This trick is a staple in algorithmic problem solving. It is a classic example of turning a naive expensive computation into a tiny number theory trick. It also helps when you need properties of factorials for combinatorics, or quickly checking properties of huge numbers without expensive computation. To wrap up, we've used a fast, memory efficient approach to count trailing zeros in factorials by counting powers of 5. The solution is compact and practical for any reasonable large n. If you'd like, I can also provide a version that handles extremely large n using BigInt for other related computations, or a short derivation proof on screen for the power of 5 formula. Which would you prefer? Thank you for watching. If you enjoyed this video, please make sure to like, share, and subscribe for more JavaScript tutorials. I'll see you in the next one.